Okay, so this will get into periodic trends. What we know so far is that valence electrons determine reactivity. And we also learned that the noble gases are the most stable. Those are the Kardashians. They have 8 valence electrons. And since everything wants to be stable, everything would prefer not to have instability and want to be like a Kardashian. Uh, they are all trying to get those 8 valence electrons. So the reason why water occurs is because the 6 valence electrons of oxygen gets together with 2 hydrogens, each bringing 1 valence electron. So now oxygen thinks it has 8. Each hydrogen will think it has 2 by sharing 1 with the oxygen. So it'll think it has 2 valence electrons like the noble gas helium. Oxygen will think it has 8 valence electrons like the noble gas neon. All right. So what we're going to do now is called the um, periodic trends. Periodic trends have everything to do with um, with attraction. So I try to get your attention by playing music, right? Because if you're at the club, then you're trying to get attracting, you're trying to be attracted to someone or trying to get someone attracted to you. And the problem is, um, can't date ourselves with this. So the problem is that there's things blocking, right? So the inner electrons are blocking the natural attraction that outer electrons would have for the nucleus. The nucleus is positive, electrons are negative. So these negative electrons sort of have, because of their real estate, better attractability to the nucleus. And these further away electrons, because they're so blocked by the crowds between them and the nucleus, are being somewhat repelled and are not as attracted to the nucleus. Okay, so we call that the shielding effect, that inner electrons will sort of repel outer electrons because they're blocking their view. So I try in a class to put on a wig to explain this to you. Um, Unfortunately, if you're on online, that's not a thing. Okay, so if everything wants to be like a noble gas and electrons, the more electrons you have, the more blocking can occur. It should make sense that the most desirable atoms for their electrons would be up in this corner because they have few rings and they're very close, or they are noble gases. So, increasing desire to keep electrons. These do not want to keep their electrons, and these do want to keep their electrons. So, and the trend travels in that diagonal fashion. So so this is because of increased shielding. Right down here, they have the most shielding. Up here, they have the least shielding. So you should have watched the Saturday Night Live where Boo Jeffries is a terrible fighter, but she plays this death fight game, and as such, even though her strengths are a relationship with her mom, her weakness is fighting. And because of that, she does not like fighting. And in this fighting game, she's not very good. But when you play these games, you should hopefully know that there are different people who have different levels of ability. And in that video that I showed, Scorponok had the high ability. Everyone wanted Scorponok, right? Nobody wanted Boo Boo Jeffries, and then there were ones in between. So electronegativity is similar to this fighting game. If an electron was thrown between two atoms, this is sort of their ranking as to how they would fight. So if you put an electron between nitrogen, which has a ranking of 3, and boron, which has a ranking of 2, what this is telling you is nitrogen will beat boron for that electron more often than not. Okay? So this actually explains why ionic bonds form between the nonmetals, which are very high in their fighting ability, and the metals, which are very low in their fighting ability. Notice hydrogen is a nonmetal, so it's much out of place here for electronegativity. In fact, for all these periodic trends, it's out of place. It should be over here, hydrogen with the nonmetals. So when you're thinking about what hydrogen should do for electronegativity or any of the other things I'm going to describe to you, please remember it's a nonmetal, so it should be on the nonmetal side of things. Notice the noble gases are not involved in this because they don't fight for an additional electron. They're already good. They got all the electrons they need. So they're stable. So they don't get involved in these fights. These are only for things trying to be like noble gases. So electronegativity is the measure of an atom's ability to attract additional electrons. So Boo Boo Jeffries in this corner, Scorponok in that corner. and that's going to be true for everything we're doing. Here is first ionization energy. Now it's the energy required to remove an electron you already have. So the noble gases are involved now. Don't you dare take an electron away from me. I already have mine, right? So very high energy. Think about if I try to take a phone from a high schooler, they fight me at no end because the phone is their life. So if you really like something, you will fight to keep it from getting taken away from you. So that's why these noble gases have high electronegative or high ionization energy. Halogens, very high ionization energy. Low ionization energy, again, the Boo Jeffries corner. They're not going to fight you for anything. You can take the electrons. It's not going to be much of a fight. So energy increases as you go across ionization energy, and it decreases as you go down. So the general trend is, again, as you go up toward helium, you have higher energy, and down in this corner, lower energy. All right. Now, the atomic radius drives me a little nuts. People always say, well, that's backwards. It's not really backwards, but let's talk about it. Cesium has the biggest atomic radius of everything here listed, and helium has the smallest atomic radius. So, as you'll see, things get smaller as you get up toward helium, right? And it's bigger in the cesium. But this has to do with attraction. Think of what we've been saying. If you're attracted to your electrons, are you going to let them run around like cesium and just let them harry carry go all over the place? No. You keep very close watch of them, and you keep them very tightly in place, and so it's harder to take one away. So atomic radius should make sense based on attraction. You can also just memorize that cesium's big and helium is small. That's fine, but I'm hoping that this makes sense to you. So think about a shepherd, right? If a shepherd is very watchful of his sheep, he will keep them in a tight circle so none can get taken away from him. That's like helium. Whereas the shepherd who doesn't care quite as much if a wolf comes and takes the sheep away, he'll have them all over the field. So think about the radius of what the shepherd's field looks like, right? Although sheep being electrons would be pretty spread out, this shepherd has a very small group of sheep uh, in a close circle. So the things that care about their electrons keep them in a close circle. The things that let them wander off don't care about their electrons so much so that they can get taken away. All right. So going down a group. So as we go down, notice the size gets bigger. Okay, helium, neon, regardless, they all get bigger as you go down, and let's describe that. As you go down, you're increasing your periods, and as you increase your periods, you're increasing the number of rings. And as you have more rings, it needs more space, right? So lithium, sodium, potassium, they're all in group one. They have the same number of valence electrons, but lithium is much smaller than sodium because it only has two energy levels, two rings, whereas sodium has the three rings. Potassium has one, two, three, four rings, right? So it needs more room for those rings, so that it gets bigger as you go down. Now, going across a period, so going from sodium over to the noble gas, things are getting smaller. Now, let's talk about that. Because you have the same number of rings, right? Period three has the same three rings. They're not going to get necessarily any bigger, but the attraction for those outermost electrons, based on that shielding effect I was just discussing, is increasing. So there's more increased attraction to your outermost electrons because there's more out there to be attracted to the nucleus. Here, there's only one electron way out there by itself. It's being shielded by the 10 inner electrons. So that's a lot of resistance for anyone to care about that electron. That's why it sort of wanders off. Aluminum versus sodium has now 3 electrons, so there's a little more out there to take care of. Argon has 8 electrons in that outer shell, so there's even more. So there's more attraction as you add more electrons to that outer shell. So as you go across a period, your size decreases, which is symboled here, right? Potassium going to krypton, those are getting smaller as you go across. That's a pretty good trend that you see there. All right, I think that's all I'm going to talk about right